What really is a vector? It's simple, right? A vector is just an arrow in space with a certain magnitude and direction. But did you know that there are at least two quite different ways of conceptualizing just what a vector is? The intuitive arrow in space idea is the common one students encounter in an introductory physics or engineering class. It turns out, though, that mathematicians have developed an alternative understanding of what a vector is, one that is much more general and precise. In this video, I will highlight the key differences in these two approaches and help you to see that the physics concept of a vector is really just a special case of the general mathematical one. So, how exactly are vectors studied in physics? Typically, a vector is defined as an arrow in space that is used to represent some physical quantity like velocity or acceleration. Since it is an arrow in space, this means that it must have a specific length and direction. So any two vectors with the same length and the same direction are equal to each other. It doesn't matter where these vectors are located or if you move them around. As long as they have the same length and direction, they'll remain equal. But as soon as you change one of these, for example, rotating one of the vectors while keeping the other fixed, they'll become unequal. The first two operations on vectors that are typically introduced in a physics class are scalar multiplication and vector addition. Scalar multiplication allows one to scale a given vector by some factor, making its magnitude increase or decrease. These numbers that multiply and scale the vector are quite naturally called scalars, and are usually taken from the set of real numbers. Vector addition, on the other hand, allows one to combine two vectors and form a third one that is the sum of the two. The steps involved in adding two vectors are straightforward. First, take the tail of one and move it to the head of the other. Then, go from the tail of the initial vector to the head of the second one. The new vector that results is the sum of the two. So, that's the basic setup when working with vectors in a physics class. Not surprisingly, mathematicians are not quite satisfied with this approach. One of the main tasks of a mathematician is to abstract from the particular and to generalize concepts so as to cover as many instances as possible. This was successfully done with vectors in the late 1800s into the 1900s when a theory known as linear algebra was developed. Essentially, what linear algebra does is provide a clear and precise way to first generalize the familiar two-dimensional and three-dimensional space that most students are familiar with to a space of some arbitrary n dimensions. This can be done with both the real numbers and the complex numbers. This notion can then be further generalized into the concept of an abstract vector space, which is an algebraic structure that satisfies a specific set of axioms. A vector then turns out to be just an element of a vector space, something that lives in this larger abstract space. Now, I also made a video on the axioms of a vector space, so feel free to check it out after the end of this video. The concept of a scalar also gets generalized in linear algebra. Whereas in physics, we typically use real numbers to scale vectors, in the theory of linear algebra, a scalar is an element of a mathematical structure called a field. The real numbers are just one example of a field. Other examples include the complex numbers and the rational numbers. This allows mathematical vectors to be multiplied or scaled by any elements that are taken from a field. So from the mathematical perspective, the conceptual difference of vectors versus scalars turns out to be one which is based on the type of abstract space each lives in. Vectors live in vector spaces, and scalars live in fields. But since the familiar 3D space that introductory physics works in is actually just a vector space with scalars taken from the real number field, it turns out that the physics understanding is consistent with the mathematical one. The physics concept of a vector is just one specific instance of the much larger general mathematical concept.